Today we would like to talk about ultra high strength concrete. This is our content page. First, I would like to introduce what is UHSC. Ultra high strength concrete UHSC is a construction material. The concrete which have compressive strength greater than 100 megapascal is called as UHSC. UHSC is composed by cement, fine sand, coarse powder, micro-silica, steel fibers, and HRWA. Steel fiber optional to increase its concrete ductility and tensile strength. The key properties of UHSC including ultra-high strength, shear strength improved, and high resistances in impacts as well as repeated loads. Also, high durability is a property of UHSC. So it is a comparison between ultra-high strength concrete and other type of concrete. So next, I will talk about the development of UHSC. So initially, UHSC developed by Pierre Richard in 1994. So the concept of UHSC is come from other type of the concrete called reactive powder concrete. In 2017, some research showed that the addition of multiple carbon nanotubes on UHSC can increase in compressive strength and flexural strength. Also, it can improve the deformation ability.
Regarding the concrete make design of UHSC, reinforcing powders is used in UHSC to increase the compressive strength and improve other properties. Various powders of UHSC must have a grain size distribution in order to produce the mix which have very high dry density. We have found that the very fine gas powder can use to improve the rheologic and mechanical properties of UHSC, as well as the using 0.01% by weight of cement GONS can result a 7.82% in compressive strength after 28 days. Concerning the use of cement for UHSC, in order to keep the good control of rheologic of UHSC and provide the good rheologic long enough pooling, CVA contains sugar over 5%, CVS contains sugar over 50%, as well as the specific surface areas of cement must be around 340 meters square per kg. This is the mixture properties of UHSC. For the mixing methods of UHSC, first, mixing powders which includes coarse sand, cement, silicon foam, and quartz coarse is treated at a constant speed of 1.8 thousand RPM for about 1 minute. Second, add half volume of water that containing half amount of superplus oxide. Also, mix about 3 minutes with the speed of around 285 RPM. Then, add the remaining half volume of water and superplus oxide. Finally, mix about 8 minutes with a constant speed of 1.8 thousand RPM.
Now, I would like to talk about the property of ultra-high strength concrete. The first one is strength. In this part, both compressive and flexural strength would be introduced. According to the experiment done by Rachel and Charisi in 1995, the compressive strength of ultra-high strength concrete is between 170 megapar and 230 megapar. Apart from compressive strength, let's look at the flexural strength. The flexural strength of ultra-high strength concrete is between 30 megapar and 50 megapar. Now, let's focus on the factor which may cause the property changes. Based on the experiment done by Yasuchi in 2005, the increasing Fa content up to 40% cement replacement would cause an increase in compressive strength value. The dosage of SSF would also affect the flexural strength. When it's in 120 kg per meter cube, it performs the highest flexural strength. In short, the composition and material proportion would affect the UHSC's strength. The second property is about UHSC's elasticity. Because UHSC's mixture contains homogeneous silica aggregate, the average elastic modulus of UHSC is around 50,000 megapar. The third property is about thermal resistance. It may help us to identify the ability of structural elements to withstand fire or to give protection from it. There are several elements that may affect the thermal resistance of concrete. The table below shows that when the temperature raises, the final compressive strength and modulus of elasticity would be reduced. We also found that when the load level of concrete increased, fire resistance time would decrease. By comparing with NSC, normal strength concrete, the fire resistance time of UHSC is more than 2 times of NSC. The last property is about shrinkage. The figure below shows that when the temperature increases, the percentage of waste loss would decrease. It shows that the volumetric changes of concrete is highly related to its exposed temperature.
The final part is the applications of the UHSC, and the first application is the structural strengthenance and retrofitting. The UHSC have a less performance in durabilities and the mechanical properties, so it can increase the strength and the life expectancy of the infrastructure. This technology has been widely used in different kinds of the infrastructure, such as highway, river tunnel, and the water dams. The next application is the bridge girders. The UHSC have a very high compressive strength and it can bear a very heavy load, so it can replace some of the materials such as steel bar or the reinforced concrete to become the bridge girders. For example, such as the footbridge or Peace in South Korea or the March Hill bridges in USA. The UHSC bridges have become more and more popular in the world. As the picture shows, the North Americans and Malaysia are building more and more UHSC bridges in the last few years. Next is the applications on building. The UHSC can actually provide a nice visual appearance to the building. Such as the museum and the football stadium in France, their roof and the cover are actually made by the UHSC. Finally are the applications in Hong Kong. Because of the high investment in manufacturing facility, the high material cost, and lack of demand for advanced concrete technology, the Hong Kong applications on UHSC are actually very low. The concrete used in One Island East actually have the most compressive strength in the Hong Kong building. However, the compressive strength are actually 100 megapar, which is actually a very low level by comparing to other UHSC building in other countries. This is our referencing. Now is the Q&A session. Feel free to ask if you guys have any questions.